Yeah, thank you very much, Andrei-san. So, yeah, I'm a professor at the University of New South Wales in Sydney, Australia. And yeah, that's my actually second visit here. So I'm kind of very happy to be back after about a year. And today I'll be talking about bimerons and antibimerons, and I'll discuss physics and also some potential applications. So basically, these applications will be kind of motivation for my work. And so yeah, let me start with this. Oh, by the way, please feel free to stop me with any questions if you have any. Actually, I think it's froze. Not sure.
Not that. I think maybe it's still on the.
Oh, okay. Okay.
And once we press that one time, it should return back to the. There we go.
Yeah. Okay. Yeah, it works now. Yeah. Yeah. So, so motivation for this work in general, kind of new memory and logic devices. So basically, we want to substitute these bulky hard drives with something which will be faster, smaller, and lower power. And especially low power, I think recently plays quite a big role, because I learned recently that, well, probably many of you using ChatGPT. So apparently, if we polite and we like say something like thank you or please, and yeah, especially like in Japan, people are very polite when they write. So then that apparently costs extra, $100 million in electricity usage. Just say extra please or something. So that's why definitely we need some devices which will be low power. And yeah, so let me kind of present historically what was kind of happening on this route. So basically, the first idea in this direction was introduced by Stuart Parkin, who suggested. Sorry, I think I have a little bit of an echo, but hope you can hear okay. Yeah. So. Yeah, so this idea of Stuart Parkin was to use this ferromagnetic wire, and then if you apply current, so then and then when you apply current, then you can move domains with which here represented by blue and red color, which kind of magnetization domains with magnetization up and down along this wire. And so the idea is that, yeah, if you have some other device attached which can read this information and also create this type of domains, so that can be a memory device. And then there were also ideas how to make these devices more dense, right? So it's like, for example, using this 3D stacking idea like shown here. But what was later realized that actually there are quite some issues in this direction. And one of the main ones is that it's very hard to make the smooth wire without any surface roughness. And actually, if there is a surface roughness, then it can uncontrollably pin these domain walls. So the next idea in this direction was to use, instead of domain walls, which are extended objects, which extend from one side of the wire to another, using kind of particle-like objects which not necessarily touching the like edges of the wire. And so that was the idea to use skyrmions, which also topological objects. And well, I think probably many of you know them here. So I will not go too much in details now. But basically, the idea is that these are topological quasi-particles. And well, if we apply current, so we can move them along this ferromagnetic wire. But then later on was realized that that's not kind of the full story, because actually, whenever you apply current, there is also sideway motion, well, which is due to Hall effects. So in this case, it would be Skyrmion Hall effect. And so then that would be rather parasitic effect for this memory device because, well, these skyrmions which serve as bits of information, they would kind of roll off the edge of the wire and well, disappear. So that would be not such a great idea in general. And so in my talk today, I'll talk about other topological spin-textures like bimerons and also antibimerons, which I'll introduce to you soon to solve this problem. And also I'll talk about different materials because, well, actually these wires originally were thought to be ferromagnetic, but if they're ferromagnetic and if you do this 3D stacking, then, well, it's kind of hard to put them too close to each other because in this case there are parasitic effects of stray fields from one wire on the other wire. And well, I'll tell you that it's maybe better to move to antiferromagnetic spintronics or topotronics, basically using instead of ferromagnetic wires, antiferromagnetic wires. And also I'll show you that there is quite a lot of universality in dynamics of spin-textures in antiferromagnets. And so finally, I'll also talk about some combination of things which I discussed. So basically, I'll talk about these domain walls, but actually in this case, these domain walls will be an antiferromagnet. And well, I'll show you that it's possible to create these analogs of skyrmions, which are bimerons, on these domain walls with current pulses, and also move them along this domain wall. So basically using them as kind of highways for information processing. Okay, so yeah, that will be roughly the plan. And yeah, so now just kind of to start with, so let me, yeah, I already mentioned that there are different topological spin-textures, not only skyrmions, and I know that probably many of you here working on some of them. So let me just kind of remind you that there is a variety of them. So it all depends on what kind of magnetic interactions we'll have in the system. And if we consider thin films, so we can look at kind of pseudo two-dimensional objects like skyrmions or anti-skyrmions, and there are some others. So basically, yeah, in systems with, let's say, frustrated interactions, you can have higher order skyrmions like the one shown here as topological charge +2, and so on. And well, of course, this bimeron, which I'll discuss kind of much more in the next few slides. But yeah, you can also have, let's say, skyrmionium and so on. But you can also look at different type of materials, not only ferromagnets, but also ferrimagnets. So then you can also stabilize this type of spin-textures. And also you can stabilize them in antiferromagnets as well. So if you have two sublattice antiferromagnets, so basically on each sublattice, you would have this ferromagnetic topological spin-texture. But overall, this spin-texture will be antiferromagnetic then. And so finally, yeah, we can also consider truly three-dimensional textures. Well, not like in thin films like this first two rows. And again, the simplest example would be just extend, let's say, skyrmion in third dimension, in z dimension, and then then we'll get a skyrmion tube. But so now it actually would depend on how our magnetic interaction scale with the thickness. And if they actually change, so then you can get, oops, sorry. Then you can actually get more interesting objects like the chiral bobber. So basically, it looks like skyrmion on the surface, but if you go in the bulk, because magnetic interaction changes, so then it would terminate with the Bloch point in the bulk. And of course, you can also have like kind of pure like Bloch and anti-Bloch points in the bulk, and you can even form crystals out of them. And well, maybe the most fascinating recently studied the 3D topological object is a Hopfion. So yeah, here I showed some kind of simple example, and yeah, I know that there is quite some work done here also on Hopfions, but not in ferromagnets or in the ferromagnets, but in liquid crystals. So yeah, there is here kind of a lot of connections with other areas of condensed matter physics where these topological textures can arise. But in my talk today, I will concentrate on magnetic systems. And yeah, let me maybe just a little bit talk about 3D system, but then eventually I will switch to this bimerons and antibimerons. Basically, I'll switch back to thin films. Yeah, but yeah, so let me just kind of mention about the three-dimensional textures here that, well, I already mentioned that it could be chiral bobber can be observed in ferromagnets, but, well, recently I was involved from theory side in experimental effort at the University of New South Wales, where they actually observed the chiral bobbers in topological antiferromagnets. So here there is kind of extra interest because in this topological antiferromagnets, so in this case it's MBT. So in this material we also have, so it's a vial semimetal, so basically we have non-trivial topology in reciprocal space. So interest in this material also kind of related to the fact that you can well, kind of crossbreed topologies in real space if you have topological interactions in this material and in K-space. So, and the question if these topologies can affect each other. So here I just present maybe like first step in this direction. So basically that was imaging done of the chiral bobbers. But basically what I want to point out here that because it's antiferromagnet, so the chiral bobber actually has a bit more interesting shape than in antiferromagnets. So sorry, than in ferromagnets, because in antiferromagnets at the interface, the Lashinsky-Mori interaction changes. So as a result, yeah, maybe it's kind of easier to look at this kind of 3D picture layer by layer. So you see that on top layer, the skyrmion, this actually ferromagnetic skyrmion is smaller, then it's getting larger and so on. Yeah, maybe another thing I should mention here. So it's a layered antiferromagnet. So it means it's actually kind of there are stacks of up and down like layers, ferromagnetic layers, but overall the material is antiferromagnetic. So as a result, well, yeah, you will see these layers with ferromagnetic skyrmions, but kind of alternating direction of magnetization in them. And well, eventually, like in the bulk, deep in the bulk, it will terminate with a Bloch point. Okay. And well, yeah, another interesting thing that basically they formed usually on domain walls, and I'll come back later to this point, but basically, well, domain wall is already partially topological object in transverse direction. We kind of change topology, so it's actually, that's why usually it's easier to create this type of spin textures on the domain walls or in the places where the domain walls disappear. Because actually what happens in this experiment, well, they change magnetic field, and as a function of magnetic field, this domain walls start to disappear and break into some bubbles. And first they thought that they may be skyrmions, but then we realized that these are actually the chiral antiferromagnetic bobbers. Okay, so yeah, because I want to tell you about several topics, so let me actually kind of switch back to more two-dimensional textures. So basically now I want to consider thin films, and so now I want to kind of look at in plane magnetized textures which analysis of skyrmions. So yeah, skyrmion is, as I already said, that's this topological spin texture in out-of-plane magnetized material. So yeah, here the background, let's say magnetization everywhere perpendicular to the plane and pointing up. And yeah, so basically from the center of the skyrmion where magnetization is pointing down, it's basically everywhere continuously rotates from down to up in all directions. And so that will be a skyrmion. So now, how can I get a bimeron here? So if I just naively rotate all the spins by 90 degrees in plane, let's say along x direction, so then I'll get this spin texture. So, well, we call it symmetric bimeron. Well, because, okay, so first of all, yeah. Well, as you see, there is a symmetry between these two objects, blue and red. And these blue and red objects are actually two merons. So it's two, one of them vortex and the other one anti-vortex with opposite polarization. So basically in the core of one of them, magnetization pointing up, and the other one pointing down. Well, these merons are strongly coupled to each other. But okay, I kind of naively said that we can rotate magnetization by 90 degrees. I mean, of course, in real life or experiment, you cannot do this. So it's a bit more complicated. So in this case, well, actually, you need to have system with in-plane anisotropy, let's say along this x direction, and also magnetic field along x. But also you need to change Zaleshinsky-Maury interaction. So basically, you need to rotate vectors of Zaleshinsky-Maury interaction, let's say along this axis by 90 degrees out of plane. So yeah, that this, I hope you can see this red arrow. So that's represents this arrow. Red arrow represent Zaleshinsky-Maury interaction vectors between magnetic atoms. So that's Zaleshinsky-Maury interaction, interfacial Zaleshinsky-Maury interaction, which stabilizes the Snell skyrmions. But yeah, if now I rotate along this axis all these vectors by 90 degrees, like shown here, out of plane, so then this type of Zaleshinsky-Maury interaction would stabilize the symmetric bimerons. And yeah, you can also, well, stabilize bimeron crystals like the same way as skyrmion crystals stabilized, well, in certain range of parameters. And yeah, just maybe for completeness of the picture, if I rotate now, again, along the same axis as DMI vectors by another 90 degrees, like shown here, so then this Zaleshinsky-Maury interaction would stabilize anti-skyrmions. And yeah, I can also have anti-skyrmion crystals. But actually what we realize that, well, this type of Zaleshinsky-Maury interaction is rather exotic. So, well, so far, well, we don't know any material which would actually have it, and as a result, stabilize the symmetric bimerons. So, well, we started to think of kind of some maybe other possibilities to have bimerons, and I'll tell you now about this full classification of these objects. But maybe before that, let me also kind of answer the question: so why bimerons can be more interesting than skyrmions in this sense. So one of the reasons is that, well, by systems with bimerons, they possess like pure topological Hall effect. So what I mean by this is the following. So let's say, let us consider a skyrmion and system with a skyrmion. So that means that in the system, magnetic field and magnetization are generally out of plane, and also emergent magnetic field coming from this non-trivial topological textual skyrmion, also pointing out of plane in the same direction. So it actually means if, well, we will do this whole measurements. So basically our transverse resistivity, like this rho xy, that would have three contributions. So it will have this ordinary Hall effect coming from magnetic field, this anomalous Hall effect coming from magnetization, and also, well, this topological Hall effect contribution coming from the emergent magnetic field. But it's very hard to disentangle all three of them. Although, again, there are quite significant efforts in this direction. But what we offer is that if we consider a bimeron system, then, well, because magnetic field and magnetization are in plane, so in this case, well, basically, we will not have these two contribution. And in this case, the measurement will be given like pure topological Hall effect rho xy in this case. All right, okay. So now after hopefully motivating you enough that bimerons can be interesting, so yeah, let me finally give you a full classification. As I already mentioned, so that depends on type of isolation-scheme interaction. So yeah, this one, which stabilizes the symmetric bimerons, so that's, as I said, it's rather exotic. But then later on, well, we studied different ones, the isolation-scheme interaction. And yeah, I know that, well, Leonovson was also quite involved in this type of studies too. So, so basically, but in our terminology, well, we call it these textures asymmetric bimerons. So why? So basically, if you look at this texture, well, it's clearly asymmetric, but also if you look in the centerpiece, so if you look more closely, you will see that it will be a magnetic vortex. And this blue object, this crescent shape like that, that will be anti-vortex. Okay, so that will be asymmetric bimeron, but then we realized very recently that for different type of isolation-scheme interaction, like the one shown here, and actually the one which stabilizing also anti-skyrmions, like what I showed you on a couple of more slides earlier. So in this case, well, we can stabilize a different texture, which we call asymmetric antibimeron. And the reason why we call it, because, well, this now red object in the middle, if you look more closely, you will see that it will be magnetic anti-vortex. And in this case, this blue object, it will be crescent shaped like vortex, okay? And yeah, maybe another reason to call it antibimeron, because it's also stabilizing and anti-skyrmions, the same DMI. Okay, yeah, so now let me, well, because that's kind of brand new object, so let me talk a little bit more about this. So basically, to stabilize it in simulations and consider it analytically, well, we can write down the following minimalistic magnetic free energy or Hamiltonian. So yeah, here again, the most dominant term, of course, will be just exchange interaction or symmetric exchange. And then, well, we need to add this isolation-scheme interaction, the one which stabilizes anti-skyrmions as well. So basically the one shown in this picture. And so basically, in order to have this isolation-scheme interaction, well, basically you need to have a material with D2D symmetry. Okay, and there are a couple of candidates already, experimental candidates. So, for example, this Heusler alloys, like shown here. So that's materials where anti-skyrmions were already observed. And yeah, so finally, in order to stabilize, well, this in-plane magnetized object, so we also need to have in-plane magnetic field, well, along x-axis in this case, and in-plane anisotropy. And actually, it could be two types of anisotropies. So here I show one for easy axis along x, but it also can be easy plane. Okay. Okay, so now what kind of properties these materials have? Oh, sorry, these textures have. And so let me start with static properties. So main actually difference is coming from asymmetry of the textures. So basically, what I'll tell you now, it will be kind of similar for symmetric antibimerons and bimerons. So one of the differences here that if now I, for example, draw a topological charge density, basically the small q, again, this capital Q, that's overall topological charge of the texture. But yeah, if I just draw this density, so you see that for asymmetric antibimeron, and the same for bimeron actually, it will be structure like the one shown here with two peaks, well, which correspond to two merons here and there on a certain distance from each other. And so actually this is very different from what we would observe for topological charge density distribution for skyrmions or symmetric bimerons. Because in those textures, you will have this symmetric distribution of topological charge density, and it will be this ring shape picture like the one shown here. So actually, because of it, well, as I'll show you later, dynamics can be very different, and actually we can explain it also analytically based on this distribution of topological charge density. But yeah, maybe you'll hear about it in several minutes later. But for now, yeah, let me also draw your attention to another interesting static property, which is kind of rather different for asymmetric textures compared to symmetric ones like skyrmions. So in skyrmionic textures, in one film, you can create skyrmions only of one topological charge, let's say +1. And so that's related to the fact that, well, we kind of fix background. Let's say everywhere magnetization will be pointing up, perpendicular to the plane. But in plane magnetized textures, actually there is a degeneracy. So we can have basically this asymmetric antibimerons with +1 and -1 topological charges, and it will cost exactly the same energy for both of them. So it actually means that in this type of thin films, we can create, well, we can have 3 topological states. Okay, no trivial state, right, with no antibimeron, and also 2 more states, the one with topological charge +1 and the one with topological charge -1. So as a result, it means we can use the system as a prototype for ternary memory and logic applications. So again, the idea of ternary memory and logic is not new. So if you will search literature, you can find some reviews, maybe like even in 80s. But and actually, it was shown that this ternary memory can be like more efficient than binary memory. But the problem, from what I understand, is more kind of finding proper experimental realization. Because the issue with ternary memory is that you have 3 states. And usually this intermediate state, what they call, is kind of very hard to control it, because basically there is a big error, kind of to, well, leak from the state to like with a left or right state. And so here, well, because well, this system offers 3 topologically distinct states, that's why we believe that that can be much better, because it's basically these 3 states will be protected by topology, and yeah, that can be much better for system for applications. But then, well, if you want to follow this route, then immediately questions rise how we can manipulate all the spin textures in these films, and how we can, let's say, increase or decrease topological charge of the system, and like change number of these objects in the system. Mm-hmm.
My question is that as a distance between the different topological charges matter, is it important to consider distance between the different?
Well, okay, so yes.
Charge?
You mean within?
In some cases, that collapses.
Right. So yeah, actually, yeah, that's a very good question, and that's exactly what I'm kind of going to talk next.
Okay.
So, but yeah, but maybe like short answer, if it's within the same bimerons, then this distance matter, if you're talking about this one. But if between bimerons, it doesn't matter, I guess, as much, as long as they like not too close to each other. So then, yeah, we're not really taking it into account. Okay, so yeah, but let's answer this question in more detail. So for this, actually, I need to, oh, sorry, maybe just before talking about this, so let me mention one more interesting fact which we realized about this asymmetric spin textures. Well, because the asymmetry, if we excite their low line modes, and let's say we use AC magnetic field, so then, well, their modes which, let's say for skyrmion, like there is a breathing mode and there is also a rotational mode, or sometimes people call it gyro mode, related to the gyrotropic force. So they usually decoupled, but here they are kind of strongly coupled to each other. So basically, because of this coupling of breathing and rotational modes of these asymmetric objects, we have not just kind of one resonant frequency on which we excite them, but there are usually like few or several of them in a kind of reasonably narrow range. And again, for ferromagnets, that's usually like several megahertz. We also did similar simulations for antiferromagnets, and then it can shift to sub terahertz. But basically, here, what I'm showing that, yeah, you can roughly see this type of modes, but because there are several of them, so it actually means we can use the systems as nano-oscillators, and nano-oscillators which have several resonant frequencies. And so that's, we believe, kind of maybe nicer system than what was proposed earlier. And yeah, partially we also worked on in this direction. So we, for example, we were proposing to use the skyrmions or bimerons in a disk when they kind of involved in rotational motion. But in this case, there is only one usually resonant frequency, and all these objects are also moving and affected kind of by how perfect shape of this disk as well. But in this situation, well, we have no kind of really moving parts that much. And yeah, as I said, there are several resonant frequencies here. Okay, yeah, so now just kind of to answer more detailed your question. So in order to answer this, well, I really need to consider dynamics in this case. And well, maybe just kind of few general words. So for simulations and in general, to treat it analytically or kind of any magnetization dynamics, well, people use Landau-Lifshitz-Gilbert equation presented here. So that's basically equation for evolution of magnetization M. And yeah, this first term is effective magnetic field term. So basically it represents rotation of magnetization M around effective magnetic field. Let's say effective magnetic field points this way. So then magnetization will be precession around it. And next term, it's Gilbert damping, because again, we always have some coupling to phonons or some other, well, external system and so on. So, and because of it, we'll have damping in the system, and this damping, basically, instead of this infinite precession, it will eventually, this precession will die out, and magnetization should point along the effective magnetic field, unless, well, we have some external drive, and this T, it's external drive. Well, in this case, again, due to electric current, and yeah, we apply current along X direction here. And yeah, so here we consider spin transfer torques, but yeah, we also kind of consider spin orbit torques in other more complicated systems. But anyway, so you know, what happens here? Yeah, oh, maybe kind of last thing to mention that, yeah, so generally for this spin transfer torques, this non-adiabatic spin transfer torque is more efficient, this one, and beta is a constant coefficient of this non-adiabatic spin transfer torque. So generally, for all this type of dynamics, you kind of need to consider ratio of Gilbert damping alpha and beta, and that's why, well, you will see results basically for different ratios of alpha and beta when one of them is larger or smaller than the other one. But okay, that's maybe a technical detail. So let me concentrate on the case, let's say when alpha greater than beta, like this one. So in this case, let's say if I consider now two asymmetric antibimerons, one with topological charge +1, and the other one with -1, and I apply current, so you see that one of them is actually increasing in size, while the other one is getting a bit smaller. It shrinks a little bit, but then it's kind of stays usually the size, and that also represented on well, kind of this picture. D is the distance or kind of transverse size of these textures. We'll say this blue one corresponds to this one picture. You see it's more or less linearly increasing. Well, okay, so yeah, this one, that's kind of translation invariant case, like when alpha equal to beta. So that's maybe not very interesting, but yeah, it's just kind of a checking that all the symmetries of this equation are preserved. But yeah, so this case when for negative topological charge, so we see that again it kind of shrinks a little bit this distance, and then it's more or less stays the same. So yeah, a couple of things. So first of all, yeah, I can explain to you on the next slide kind of analytically this behavior, but maybe before that, so what's the message here? So basically we see that depending on topological charge, so one of the spin textures getting larger, and it actually means it's getting more topologically stable. Again, naively, you can think of it like, yeah, so it's basically if you have large topological spin texture, it means inside you have many spins which you need to flip in order to destroy it. So it would definitely cost you more energy than if your texture would be like really tiny and you have like just last few spins left which you need to rotate. And so that's like roughly exactly what happens, and you will see it later when I show you collisions of these textures. Okay, but now maybe let me try to explain analytically so why it is so, why we have this dynamics. So there are two things here which kind of we need to use. So first of all, well, this Landau-Lifshitz-Gilbert equation, that's field equation for magnetization M, right? But it's a rather complicated equation. So maybe we don't need such a complicated treatment if our texture is reasonably rigid. So in this case, I can do coarse graining of this equation. So basically kind of integrate it over the entire volume and kind of look at only on low kind of energy dynamics. So basically we're looking for dynamics of this texture, like how the center of this texture would be moving. And that's basically exactly the way how this Thiele's equation is derived from Landau-Lifshitz-Gilbert equation. And yeah, I'll talk a bit more later about it, but basically this first term is a topological term. So that's it's proportional topological charge of the texture. And the other one is kind of damping-like or drag term, and that's related more to kind of the shape of the texture. So this tensor D here, that kind of really depends on how shape of this texture symmetric or antisymmetric. And that's exactly what matters for this asymmetric antibimeron. As I already mentioned, that the topological charge distribution is like this, like shown here. And what's important here, that we have actually here two merons. And actually each meron is elliptic shape, has elliptic shape if you look more closely. And well, this upper meron, it's rotated by like 45 degrees you know, compare it with respect to x-axis. And the lower one, you see tilted down by 45 degrees, so minus 45 degrees. And again, well, I will not show you kind of all derivation now, but basically this tensor, its off-diagonal component, they are proportional to sine of 2 delta, where delta is kind of angle of this tilt of this ellipse. And actually for symmetric textures like skyrmions, basically these off-diagonal elements would be 0. So that's why this type of dynamics you will not see for symmetric textures. But also actually what it means that now I can treat, well, this whole texture like two merons which are weakly coupled. So basically I can introduce some sort of spring coupling between these two merons, and then I can write down Thiele's equation for each of them, and especially when they start moving away from each other, then I can even neglect well, this coupling between them, and it still would be a pretty good approximation from what we see comparing it to numerics. But again, long story short, the point here is that depending on overall topological charge, well, here, kind of, if I look at all this kind of forces all together, that Magnus force here sometimes pointing kind of outwards on each meron and sometimes like towards each other. So when it's pointing outwards for one topological charge, so then we actually do see this expansion in, 3 minutes. Oh, okay. So yeah, I'm actually somehow very slow. So yeah, so but basically, yeah, by doing this, we can really explain all this dynamics and yeah, okay, I realized that I was actually very slow. Sorry about this. So yeah, so then let me talk about now collisions. So basically, if we apply current along X or Y direction, we can have different collisions here. And what you can see is that when you apply current along Y direction, then we can just kind of destroy the textures. So it does not change kind of number of spin textures in our system. But if we apply current along X, so then actually, well, we can, depending on topological charge of them. So as I already told you, that bigger one more stable and smaller one less stable. So when they collapse, this bigger one survives and small one getting destroyed. So as a result, we can actually change topological charge of the system, and we can also increase it, kind of make it more positive or more negative in the system. But yeah, sorry, because I'm kind of was apparently quite slow. So yeah, so that's conclusions for this ferromagnetic part. But okay, let me just say maybe like few words for a couple of minutes about antiferromagnets. And again, antiferromagnets in general can be pretty interesting because, well, in these systems, stray fields are severely suppressed. So that's one advantage, but also kind of dynamics of the spin textures can be very interesting. And yeah, so yeah, maybe just to mention in general things that because it's antiferromagnet, so we need to consider instead of magnetization as order parameter, Néel order parameter, which is difference of magnetization of two sublattices. And basically this capital omega, that's this Néel order parameter. And if I calculate now this integral, then I can get for the skyrmion, it will be something like plus or minus 1. Okay. And yeah, so what's interesting about this texture is that in antiferromagnets, they all move along the current. And yeah, we can have also antiferromagnetic antibimerons and bimerons and the skyrmions. So yeah, but because of lack of time, maybe I'll skip this. But again, so why there is no transverse motion in this case? Because again, if you'll use this Thiele's equation, which I already mentioned, and yeah, there is this Magnus force, which is perpendicular to the current, and drag force, which is along the current. So that's on one sublattice of ferromagnet. But if we consider antiferromagnet, on the other sublattice, we will have basically topological spin texture, which will have opposite topological charge, well, because we flip magnetization by 180 degrees. And that actually means that this Magnus force will also have different direction because it's proportional topological charge. So it means that this Magnus force will cancel out, and only drag force will act on this antiferromagnetic spin textures, resulting in a rather simple equation of motion where velocity is proportional to the current. And yeah, again, the same story would be for this Bimerons and Antibimerons here. And so yeah, finally, this last thing I mention is about domain walls in antiferromagnets. So yeah, so I was involved in this experiment done by Pete Wadley on the semi-metallic antiferromagnet copper manganese arsenide. And so basically here it was possible to create these bimerons on domain walls and also move them along the current along the domain wall with current. Yeah, and yeah, we believe that can be quite interesting for future applications if it will be a network of these domain walls, and then one can navigate these bits of information like this bimerons along these domain walls. Yeah, I see that Mr. Chairman is standing, so I'll just say last few words here that it's also possible to have bimerons with high topological charge. We call them bimeron clusters. And again, also in collisions, well, we can kind of change the topological charge, like shown here, you can decrease or increase. And yeah, that can be another direction where it can be used, especially because if you have long chains of these bimeron clusters, well, they act together like liquid crystals. So that's maybe some connection with liquid crystal physics here. But okay, I probably should stop here. And yeah, I'll want to acknowledge my collaborators and especially students in my group, Pavel and Yerzhan, who run the simulations, and well, Kuribayashi-kun, postdoc, who did like wrote most of the code for the simulations and also helped with analytical results, and also like my other collaborators, experimental and simulational groups around the globe. And of course, grant support. So yeah, with this, yeah, let me just kind of leave the summary, and like, yeah, I'll just kind of mention that, yeah, we now have full classification of bimerons and antibimerons in this in-plane magnetized systems, and we can describe the dynamics based on extend and Thiele's equation approach. And we also see that in antiferromagnets, the systems, they have universal behavior. Basically, all the spin textures, they don't have skyrmion Hall effect. And yeah, finally, we can also create these textures on the domain walls and move them along the domain walls with some current pulses. Okay, thank you very much, and I'll be happy to answer your questions.